Hello, everybody. Um, Welcome to the presentation of Water Supply and Treatment Engineering course 18CV46, initiated by Department of Collegiate and Technical Education. In the previous video, we have discussed about the session one. In that session one, we have discussed what is sedimentation, what are the different types of settling patterns, and what are the different types of tanks are used in the sedimentation process in the treatment of water, and some definitions. So here in the session 2, we are going to discuss about definitions, some definitions what we have discussed in the previous session. We'll recall it. It is very useful for the design purpose, and design concepts in the upflow sedimentation tank, and what are the design concepts of horizontal flow sedimentation tank. Coming to the definitions, we have already discussed this one. Again, I am repeating. This is a very important term used in the design of sedimentation tanks. Overflow velocity or overflow rate or surface loading rate. It is the volume of water passing per day per unit horizontal area. And this is that flow velocity at which tank is designed. So what is this overflow rate? It is nothing but, as I said in the previous slide, it is the volume of water passing per day out of the tank per unit horizontal area. So it is mathematically Q by AS. What is Q? Discharge volume by time. AS is surface area. So surface area into depth gives you the volume divided by time, again surface area. So mathematically surface area cancels. So what we get is depth by time. Depth by time is nothing but its unit is meter per second. Definitely it is liquid velocity. So overflow rate is nothing but it is the liquid velocity. The liquid upflow velocity is called the overflow rate or surface loading rate because water is flowing over the top of the tank into weir system. This we have discussed in the previous class. Again, as this is useful, I am repeating it. Detention period, it is the time for which the water is detained in the tank. Theoretical and mathematically, T is equal to volume of the tank divided by rate of flow. What is flow through period? It is the actual time of travel of flow of water from the inlet of the tank to the outlet of the tank. It is always less than the detention time due to the short circuiting. You see here, flow through period is the water enters from in the inlet and goes to the outlet. It is also detention period, but actually, what actual time taken is sometimes lesser than the detention period. So, because of the short circuiting, sometimes it may go take a short route and reach the outlet swiftly. And displacement efficiency is the ratio of flow through the period to the detention period. It is generally varies between 0.25 to 0.50. Let us come to the design concepts in the upflow sedimentation tank. And circular tanks are also called as clarifiers. So, upflow clarifier or upflow sedimentation tank. You'll see a figure sedimentation in an upflow clarifier. Okay, the water is flowing from the bottom, raw water particles, and it is moving in the upward direction. So, when the water is moving in the upward direction, water to be treated is going in the upward direction. It is carrying suspended solid impurities. Our main intention is we have to remove the suspended impurities inside the sedimentation tank. So, in this design, the particles fall downward. See, when the water is moving, as the specific gravity of the water is, as the specific gravity of the particles are more than water, particles tends to settle down. So particles fall downward and water rises vertically upward. Let us take the rate at which the particle is settling is Vs. So settlement of the particles or settling velocity of the particle, let us assume it as Vs, that is particle settling velocity, and the velocity of the liquid rising is V naught. So velocity of the water is V naught and that is Vs. So V naught is nothing but, as I said, it is overflow rate. Evidently, if the particle is to be removed from the bottom of the tank and not to go out of the clarified water, means if the particles goes out of the water with the water, it's of no use. Our intentions are we have to remove the particles from the water. So, if the particle is to be removed from the bottom of the tank and not to go out of the clarified water, then particle settling velocity Vs must be greater than V naught. That is the overflow rate. In other words, Vs should be equal to or greater than V naught. See here, V naught is the upflow velocity, nothing but overflow rate. Vs is the settling velocity of the particle. If V naught is more, then Vs is not going to settle down. Therefore, the settling velocity of the particle must be greater than V naught, then only Vs will come down. Okay. So, the Vs should be equal to or greater than the V naught. If this happens, that is when settling Vs is greater than or equal to V naught, then one can expect 100% removal of particles. And if Vs is less than V naught, one would expect 0% removal because if Vs, the settling velocity of the particle, is less than the upflow velocity, definitely particles are not going to settle down. It will move with the water and will come out of the water and goes out. So one would expect 0% removal. Hence, in the successful design of a sedimentation tank, the aim would be to determine the particle settling velocity Vs and fix the overflow rate at some lower value. Often V naught is kept about. So what is V naught? It is kept about 80% of the Vs. And because we have understood Vs is more, then only it will settle. Vs is more than V naught, then only it will settle. So what we do, will find out the settling velocity of the particle. Then we will fix V naught, the upflow velocity of the liquid, in such a way that 80% of the Vs, because both are velocity. So that is what we do in the upflow clarifier. The liquid rise velocity V naught is called the overflow rate because water is flowing from the top of the tank into the weir system. That is why we call it as overflow term. This term is also referred to as surface loading rate, as is explained in the previous slides, because its units are discharge per unit area, plan area. So, what is the unit? It is the amount of water, the volume of water per day, meter cube per day, meter square is the unit of overflow rate. Mm, this term can be thought of as the amount of water that goes through each meter square of the tank surface area, which is similar to the loading rate. Okay, and I have explained this also in the previous slide. We also know that velocity of flow is always equal to the flow rate divided by the area through which the water flows. So, discharge by surface area, surface area cancels, we get depth by velocity, which is nothing but liquid velocity. It can therefore be concluded that as long as Vs is greater than overflow rate V naught, the particles will settle down and be removed from the bottom of the tank regardless of the depth of the tank. The particle removal being independent of the depth of the sedimentation tank, sedimentation zones vary from a depth of few centimeters to 6 meters or greater. So this is what you have to understand in this. So particles fall downward. Um, In this tank, again, I am going to explain. Water is, see, water to be treated is taken from the bottom of the tank. It is moving upwards. As it is moving upwards, it is carrying the particles, suspended particles. Mm, and when it is moving with the velocity of v naught, listen, and particles are settled, try to settle down because of the gravity. If v naught is more than vs, then all particles will go out of the tank. If the velocity of the particles is more than v naught, then only particles will have chance to settle down. So we have to control the velocity v naught. It is in our hand in such a way that it is 80% of the ps, because v naught is also the surface loading rate is also nothing but the velocity, the liquid velocity. This is what. And let us study the type 1 settling in detail. And type 1 settling, as explained in the previous slide, it is nothing but discrete settling. What is discrete settling? Every particles which are present in the water or impurities present in the water, it settles individually. There is no contact between the particles. Every particle, single particle, is individual. So size, shape, and specific gravity of the particles do not change with time. Settling velocity remains constant. So, when a particle is settling in the water or suspended in the water, or if you drop a particle in the water, understand, it initially has two forces acting upon it. What will happen if you drop a small particle which is heavier than water in the water? It naturally flows downwards because force of gravity is pulling it. So particle is subjected to uh, force of gravity, understand, and at the same time there is a force called buoyancy or the buoyant force, understand. It is also pulling it or lifting it up. Okay, so force of gravity, I've taken it as rho g into Vp, and buoyant force is rho into g into Vp. So if you take this resultant force, F net is rho p minus rho into g into Vp. This net force becomes the driving force. So net force is going to pull the particle in the downward direction. Once the motion has been initiated, a third force is created due to the viscosity of the water. That's called the drag force. It is quantified by Ft into Cd into Ap into rho v square by 2, where Cd is the drag coefficient, Ap is the projected area of the particle. So, because the drag force acts in the opposite direction to the driving force and increases as the square of the velocity, acceleration occurs at a decreasing rate until a steady velocity is reached at a point where the drag force is equal to the driving force. So, this you have to understand. So, initially, particle is subjected to two forces, force of gravity and the um, buoyancy. Then a motion starts. Once that starts, a drag force will be created due to the will be applied on the, or a drag will resist the motion of the particle, and because of the viscosity, understand, when these two become equal, then particles start settling in a velocity. So when the drag force equals the driving force, what we have is rho p minus rho into gvp equal to cd into r p square by this one. See, this is the drag force, this one is the force which is put in the acceleration. Okay, so for spherical particles, that we know that it is oh, pi dq by 6, and ap is pi d square by 4. Thus v square is equal to 4g into rho p minus rho into d by 3 into cd r. So expression for cd change with the characteristics of different flow regimes. For laminar, understand that constant d is 24 by re laminar, and for transition it is 24 by re, 3 by re 2.34. Then for cd is zero point 0.4 for turbulent flow, where Re is the Reynolds number. You have already studied this one in the fluid mechanics. So finally, we have Rv is equal to rho v d by m. Reynolds number is less than 1 indicates laminar flow, while values greater than 10 indicates turbulent flow. Intermediate values indicates transitional flow. So for laminar flow, the terminal settling velocity equation becomes v is equal to rho p minus rho into g d square by 18m. This is known as Stokes equation. So where v is nothing but settling velocity of the particle. This is given by this for spherical particles. So this is this one. You have to what you have to understand is in the type 1 settling, when a particle is dropped into in a water, it naturally flows downwards due to the attraction. So the forces acts on that is force of gravity and the buoyant force, and finally you get a net force, rho p minus rho into gvp, which vp is the volume, the velocity of the particle. Sorry, velocity of the particle. Then a motion is initiated. When the motion is initiated, again another force will come into picture, which is called as drag force or the resistance force due to the water. Okay, where CD is the drag coefficient. Okay, and AB is the projected area of the particles. So drag force must be equal to the force acceleration that occurs. Okay, so we are going to equate these two, and after doing the calculation, finally we reach an equation where V is equal to rho p minus rho into GD square by 18m, which is known as Stokes equation. Now let us see we have discussed the vertical clarifier. Now let us see what is the design concepts of the horizontal sedimentation tank. Horizontal sedimentation tank is designed based on three assumptions. Particles and their velocity vectors are evenly distributed across the cross section of the tank. That is one thing you have to keep it in mind. Liquid moves as an ideal slug. So a layer of enters, then it moves along the length of the tank. Any particle hitting the bottom of the tank is removed. So these three important assumptions are done. Particles and their velocity vectors are evenly distributed across the tank cross section. Liquid moves as ideal slug down the length of the tank. Any particle hitting the bottom of the tank is removed. Here you can see a settling tank, a rectangular settling tank. The water is entering from the left side. Understand? This face is A, this face is B, this is C and D, and A inlet zone it enters and it moves and goes out. So this AC, this portion is the cross section, and AS is nothing but L into B is the surface area. You have to keep it in mind. L into B, H into B is the cross section, and volume is B into L into H. And you can see here A is the inlet zone where the water enters, and we have to um, mm, construct a buffle wall there so that the particles are disturbed. Mm. Then B is the settling zone here where settling takes place. C is the outlet zone and the D is the sludge zone. So inlet zone incoming flow is uniformly distributed over the cross section of the tank. B is the settling zone. The concentration of each size particle is uniform throughout the cross section. Outlet zone, it is the clarified water or the treated water is collected and discharged through the outlet over here. And sludge zone is the settling zone is the where it provides the collection of suspended impurities present in the water. Now I'll show. Let us see how a particle is going to settle down in the rectangular sedimentation tank. An inflow is there, inlet zone, and it is uniformly distributed. Particles are moving in the horizontal direction. So when the particle enters a point A, this particle tends to settle down. Means it is because of its gravity, it is moving in the downward direction. Okay, and as the water is flowing in the horizontal direction, so it is subjected to two forces. One is the horizontal force, which is Vf, and its gravitational force Vs. So the net resultant will be taken as A to C. Let's assume it is A to C. So it moves in the resultant direction. Okay. So if it reaches the bottom of the tank before C, then particles are going to be settled down. If it is not going to hit the bottom, it will go out of the outlet zone. So in the rectangular sedimentation tanks also, when the water flows in the horizontal direction, particle is subjected to horizontal flow velocity and a vertical settling velocity. So a net force or a resultant force or resultant vector you are going to get, and it takes it um, resultant direction. Okay, and if it is AC below within the AC, this direction resultant vector, then particles are going to settle down. Now, I'm going to explain again this one. Now, let us consider a discrete particle which enters the tank at the bottom of the basin, at the top of the basin at point A, and at full height h from the bottom. See here, a particle is going to enter the top of the tank. Here, a particle enters. Height from the bottom is h. Okay. Such a particle will have horizontal flow velocity Vf because water is flowing, it carries the particle, and a downward vertical velocity. Obviously, this particle has to settle down in the tank. The resultant must, in extreme case, has to move along AC. This is what extreme case resultant pole. Within this, if it comes, it will fall down. So that particle touches the tank bottom before reaching the outlet. So if you take the geometry of this one, Vf horizontal force Vs is one, Vf by Vs is equal to L by H. So Vs is equal to Vf into L by H. Mm, okay, then that is equal to Vs is equal to Q by H into H by L. You rearrange this one. Q by Vh into H by L. What is Q by BH? What is BH? HH cancels. Q by you get BL. What is BL? Breadth into length, which is nothing but surface area. I'll show the back slide. See here. S. This B. This B into L is the surface area. Q by AS. So where AS is the surface area, not surface alone, right? It is the surface area of the tank. Therefore, Q by A is nothing but overflow rate. It is the overflow rate. What you can understand here is all particles with the terminal settling velocity greater than or equal to Vs are removed. So here, based on this one Vs, if it is the terminal settling velocity is greater than or equal to Vs are removed. Only part of the particles with settling velocity less than Vs are removed. See, it is the advantage in this say this one. Even the very fine particles with small settling velocity, they are going to be removed in the rectangular sedimentation tank. So partial removal of the particles with lesser settling velocity are also removed in the rectangular sedimentation tank. So this is what this one, the references what we use. Thank you.